to Controllogix by Alan Bradley and other Logix 5000 platforms. So you'll see later on that Logix 5000 is a group term. So under this, we will have several different family, or a family with several different types of PLCs, varying in different sizes. But we'll have a look at that as we get, I think, the 2, 3, 4 slides along. So we'll focus on this platform, the Logix 5000 platform, with also the corresponding software that we'll be using. And this will then teach us how the whole Alan Bradley family works, the PLC family, and how we actually program them. But first, before we go, just some very rudimentary introductions to normal control systems, and why we actually, throughout the development of automation engineering, actually developed the device that we know today as the PLC, or the Programmable Logic Controller. So, traditionally, a control system, even in the old days, consisted of something out in the field with some connection to a controller, and then something out to the field again. Now, these two things can be closely located, like the field transmitter and the control valve in this particular example, or they can be at completely different locations. It doesn't matter. The thing is, the controller is the one element that links them both. So what happens is you have a flow of information from the transmitter, so it's a sensor relaying information to the controller, and the controller then does processing, does some math, some logic processing. Then it sends a command to the actuator, in this case it is a valve. Then something will happen in the plant or the system in reaction to this variable that has changed, or in this example, the valve position, and then it will come back, will be measured by the field transmitter again. So in this case, then you can clearly see that we have a closed loop control system, and the field controller then in this case will be, at the end of the day, be represented by or implemented by a PLC, which is a Programmable Logic Controller. So why have they become so widely accepted? They can do many things. They're very versatile. They can do a lot of input-output control simultaneously. So they are really multivariable devices. Some can control several tens of thousands of variables, both input and output, at the same time. So it is a very versatile device, flexible as well in terms of the control logic. So, for example, maybe you want to change some logic flow in your control system. That's easy. With PLCs, you simply change the program. You simply change the software. No hardware connection needs to change. So in the old days, before PLCs, hardwired relay switching was used. So the same kind of logic was implemented in relays or contactors back in the day. And if you had to change something in the logic, you had to change the wiring. Now with PLCs, of course, you don't have to. You simply change your program, which is typically ladder logic. We'll see in a while what that is, and then the whole program, the whole behavior of the control system has changed. Okay, so it's very fast. It reacts within milliseconds, sometimes microseconds. It's reliable. We spent some time discussing this in the first webinar. The reliability of these systems, simply because of the way they've been designed. They have very reliable components, very reliable processors and memory, and the way they've been constructed is simply extremely reliable. You get even more reliable PLCs than the normal, the standard ones, safety PLCs. We just had a chat last time on the statistical fallover time, and for safety PLCs it can be 1 in 1,000 years or something like that. So depending on the design and the cost, and Then, of course, if you build it into a system, you also add redundancy, then increasing the system reliability even higher than the individual PLC. But we're focusing here on the PLC reliability. Okay, it's cost effective. They are expensive devices, but if you look at the overall system cost or the plant cost, it's really cost effective. And then we can have, with a combination with SCADA systems, we can have very efficient human-machine interfaces with graphical representation of what's happening in the plant. So a very nice diagram. In this case, we have simply an input and an output. Input is a switch panel, and the output is an electric motor. So we do not have the speed change here. We simply have an on-off control with a status indicator, red or green, just good or not good. And then what the user will do is just press the button. It's not as simple as simply relaying the command to the output. The PLC is intelligent. It will have a program with some logic inside, and this logic will monitor different things. Maybe it's a pump connected motor. It will look at all sorts of things like pressure in the pipes. Maybe there are pipe leaks, leak detectors, tank levels. Maybe it's not necessary to switch on the pump because the tank's already full. You know, all sorts of things can be programmed into the PLC to decide, are we going to switch on the output or not? So there's an evaluation function taking place. So you have built-in intelligence. Simply, it's not on-off control. You have this intermediate step, which is a little bit of a brain in giving you some intelligence in your system. But more than this, PLCs can also implement speed control or multivariable analog variable control. So the ability to perhaps do variable speed drive control. You do have actually VSD modules that you can slot into the PLC rack, performing that particular function. So a PLC consists of several building blocks. Right in the heart of the system, we have the CPU, and then simply a microprocessor-based system. So the heart of where all the processing takes place is a microprocessor with a very stable operating system. And then it's got program memory and it's got data memory, with of course a data bus communicating from one to the other. Then it has modules. It has input modules, highlighted there for you in magenta, and then in blue I'll highlight the output modules. So here they are. And if you look at the picture in the previous slide, you can see over there we have these modules clearly indicated in the picture, in the photograph. They simply look like these devices. They all look at this, so they have the same form factor, the same dimensions, and they just swap, or they just slot into the rack. So what's inside, of course, is different, but the modules, they look and function the same in terms of connection. So you just slide them into the rack. At the back, it has the automatic connection, connecting the power and the bus to the module. Now the modules themselves are then connected to field devices. In this case, on the left here, we've got digital input devices. You've got a toggle switch over there. We use this naming convention I for input, and then slot 1, and then the channel number is 0. So in this case, the channel number is 7, and the slot number is 3. So in this case, also a push button that is normally closed. In this case, it's a toggle switch that is normally open. So yeah, just two examples of input devices. On the output side, in this case, we've got a resistive element. Over there, we've got a switching element, or a lamp. Okay. Now, what the CPU does, well, as we said, it's a microprocessor-based system. It reads inputs, then it does processing, and then it sends commands to outputs. And it just does it all over again in a loop fashion. So it's a round-robin type operation. It never ceases. And we'll later see when we look at the Allen Bradley specific implementation. There are other means of doing this in task definitions. We will see later. Maybe I'm not sure if it's it's in this. It's in module 1. We will have a look at 3 different types of tasks. But the default is actually the continuous type, so it just keeps on running forever. Okay, I can do arithmetic, manipulate data, and Boolean. It's actually from the ground up. It's been designed historically to perform the Boolean type calculations with if this then that type calculations, and also AND gates, OR gates, and so which was common in control in automation type systems, and also today it's still very common. But the analog part has also increased in popularity over the years. But it can also do this. It can do both analog and digital manipulation and control. Yes, and then the memory aspect, we just had the 2 different types of data. The first is volatile data, that's like variables or measurements or control variables being written to the output modules. And the other type of memory is the program that's non-volatile. It keeps, it retains the memory even after the power has been switched off. Another quick picture, we've got now 4 digital inputs. So it's a digital I/O example. This is a PLC rack. The digital input modules are connected, or one module connected to 4 channels. And they are all toggle switches normally open. Then we've got the processor and the output modules. They're also digital. K for coils, and S for solenoid valves. Power supply, and this forms the rack. The rack itself is in this blue block over there, and this part there is the rack. So that's everything that's inside. All the other things that you see on the diagram, they are external to the rack. So then on just moving along to an analog example, we see then some analog transducers, temperature, flow, and some more temperature transducers. In this case, it's 4 to 20 milliamp, which is an industry standard. It can also be DC voltages or AC voltages. There are several different combinations available. Once again, the modules, but now they are analog input and output modules, and the power supply process is still the same. We also have now the analog outputs, where we have damper actuators, valve actuators, and so on. And also there can be speed references to VSD, external VSD controllers to control motor speed. So that will be analog input output. Of course, then in a typical system you'll have a combination. You'll have more modules than just this one. You will have quite a bit of digital modules, some analog, and some other maybe specialized modules as well. Okay, so this is what actually happens. You've got the I/O system where you have the input and output modules, and they interface with the field devices. Now usually they're also isolated, so they protect the PLC against any spurious voltages or transients. The programming, this sits in the non-volatile memory as part of the PLC, the controller itself. And in combination with an external computer, the programming takes place where the program is actually then being written to the PLC. And the communication system is where the communications takes place. Also, communications to other systems. So maybe after programming has taken place, okay, you remove then the external programming computer or laptop, then there might still be communications running from the PLC rack, maybe to a SCADA system or a remote monitoring system or a second PLC system, like perhaps a plant PLC, and maybe this is a remote PLC. So there's a lot of communications going on, and this will be handled by communication systems or specific specialized communications modules. Now, the Logix5000 family consists of several different types of PLCs. Well, first of all, the Controllogix, it's the picture that we've seen earlier, where we've got the modular chassis type PLC, where this is a more conventional, traditional type of PLC, where these modules just simply slide in and out of the rack. And it's modular because you can remove and add them in modules. Then you've got the compact Logix, it's rail mounted, so it's for smaller applications. It's still a PLC system, but it's just for smaller applications. The number of inputs and outputs will be less. Of course, the functionality, perhaps the processing speed and so on, will also be reduced. Then there's other specialized types, the Drive Logix system, which is embedded in a PowerFlex drive. So this is a PLC system, but it is in one physical enclosure, combined with VST, combined with the drive, doing module speed control. But it can also do several channels, several motors at the same time. Then we've got the soft Logix. This is what we will be working with in this course, is software emulation of the Controllogix system. So you can see graphically it looks very similar. We've got these modules sitting in different slots. In this case, we've got 9 slots displayed on the screen, numbered from 0 to 8. This one on the left is RSLogix. We will see this later on. It's just to link some of the software components running on the PC together, and then some other modules. This over here is a PLC controller, and over there there's another PLC controller, a soft Logix PLC. And these others, they are digital input outputs, and you also have analog input outputs. All of them can be simulated or emulated in software. So we will be doing this during the practical aspects of the course. But the languages, programming, all of it's the same. We use the Logix5000 control engine or software. So what makes the Allen Bradley approach different, or the Logix5000 approach different? Actually, historically, the Logix 5 and 50 wasn't like this. It's from the 5000 family onwards that the change came. We don't have these segregated data files as in a conventional PLC. That data is simply stored in the next available area of memory. What I'd like to highlight is the fact that it's a tagged system, or a tag-based system, which is different from other vendors, and also different from the historical Allen Bradley systems. We'll have a look at that actually in quite a bit of detail later on. But in a nutshell, what it is that you give memory locations names, or variable names, and then the actual physical addressing with the hexadecimal address locations, that's being taken care of by the software. So it just makes the programming quite a bit easier. Okay, Logix5000 is multi-language. We have 4 different languages, 4 of the 6 defined by the ISC that we have available, of which ladder logic, of course, is the most prevalent and the most popular one being used. Yes, and then the scheduling mechanism, but we will see this as well later on. Okay, another picture of the same, we just zoomed in a little bit. We'll see, just highlighting several things. The controllers are these devices over here. You can distinctly see them there. The power supply, let's make it red. It's over there on the left-hand side with a lot of vents and fans. And then you've got modules, make the input modules, or let's make the I/O modules magenta. In this case, it's not distinguished input or output. It's simply called I/O modules. But you do get specialized modules where it's only input or only output. And then we've got the comms, which is over there. Right, so, and of course the comms can be to another PLC or to a scaler or a human machine interface, whatever. So this is the make-up of a typical PLC system in the Controllogix family. So this is this family over there, which is, it can be multi-controller and it's modular. So we'll be focusing on this during our discussions, but all the other different types in the Logix 5000 family, they are all the same in their functionality, or let's say similar in their functionality. The smaller systems will have some reduced functionality, but they still are similar, and the programming language and programming platform is the same. So yes, we are going to program primarily in ladder logic. So let's have a short discussion on what that exactly is. Okay, but before we do actually program, we need to understand the problem. So what we usually do, and as engineers, we tend to build logic flow by means of flowcharts, and this is a very good tool to use, very powerful. So you can do this by analyzing the problem and then trying to see to analyze, pull it apart, look at different aspects, isolate certain logic flows. And then in a flowchart, of course, you have statements like if then else, so you have decision making. Usually this is in the diamond type form in a flowchart. So you come in, you ask a question, it's either a yes or a no, and then depending on your answer, you have different flows. So yeah, that's the typical flow of a program, a logic decision-making type flow. Then you also have looping, you have more Boolean type operations like ANDs and ORs, XORs, and so on. All of these you can combine. Now, after analysis, you can also see here that we have written one type of decision-making as an if statement. So in this Boolean / logic decision-making and looping formulation of our problem, we can move then with this plan in our minds towards programming the solution in the language that we call ladder logic. Now, ladder logic is very powerful, and it's called ladder logic because it's a graphical programming language, and it looks like a ladder. So we've got these two rails here on the left and on the right. I'm just highlighting them for you there in blue. And then we've got rungs. I'm going to highlight them for you in red. So there they are, rung number 1, or it's actually numbered from 0. Then rung number 1, 2, and that's the end of this. We've only got 3 rungs in this example. Now, in the rungs themselves, we can have different elements, and they are input-output elements. They can be decision-making. You can see here we've got branching, so we've got parallel inputs. Some of these inputs can actually be linked to outputs, so you can have a latching implementation. And you could also, other elements, in this case we've got a timer on delay, which is another element that you can simply slot into one of the rungs in the ladder. Now what happens in the PLC execution cycle is that the execution runs from run 0 to run end, in this case number 2, and then it terminates, and actually then it loops back. So what it does, it executes that run first, and then the second one, and then the third one, and then after that's been completed, it just runs back and completes another loop. And this is the execution cycle of a continuous task. We'll see that in Alan Bradley terminology, we've got tasks that contain programs, and programs contain routines, and then the routines are actually that we implement in the programming language. But in this case, it's a continuous task. It's called bottling line. I don't know if you can read this, but there's the icon for continuous. We will have a look at this just now. And this means that this program will loop. It will infinitely loop itself. So it will just keep on executing forever. So in our software then, let me just remove all of these. We have this window. This is the RSLogix5000 software. It's actually used to program physical, real hardware PLCs, but also you can use it in the software emulation, and this is what we will do. So on the left here, you have the project tree. When you open up or start or create a new project, you'll see this. Then you have these different folders with all the different elements. We'll have a look at some of these in this webinar, and then we'll build up gradually as we learn the Allen Bradley platform. We'll build on what we've learned here. So we'll just touch on the basics. Then we've got the programming window or the routine window, where we have now, in this case, the ladder logic, but the other 3 languages will also be programmed here in this window. Then we've got toolbars with the different elements that we can just drag and place on our ladder logic here. Right. The organizer, this is on the left-hand side. Over here you can see the, I'm not sure if we list this particularly, maybe in the second webinar, but let's just quickly do this. It's grouped in tasks, so you will have some tasks, then within the tasks you've got programs, and then within the programs you've got routines. Now, later on we will see that there are limitations, of course, on the number, but the larger Controllogix systems can actually have up to 65,000 routines within one program, and then several programs within one task, and then it can have also several tasks. So you can just imagine the sheer size of what you can do with one of these PLC, especially the Controllogix platforms with sufficient number of I/O modules. Okay, so on the right hand here we see the I/O configuration. It's been labeled here: digital inputs, outputs. This one over here has got a very specific name, Cola Production, just to give us a more specific name so we know what exactly is going on. Then, yeah, this is the controller section, which is global. Then we've got the tasks. So there's one task called bottling line. In this task, we've got a program called filling station, and in filling station, we've got a routine filling process. So in this case, it's one task, one program, one routine, and you can see that the task is continuously looping. It's a continuous task. But we will have a look at more of these things as we go along. So the ladder programming window, you can simply drag these elements. You can see here we've got nodes. Just highlighting one of these node pairs for you, and you can drag the whatever you need into this location, into the node location, and then you will notice when that it appears, and you can build up your ladder in that way. I did actually mention this before, so this is just perhaps a little bit of a repetition, but it's quite zoomed in. You can see we've got tasks there, task A, task B. You can look at the icon over there. Task A is a continuous task. I think we list this on the very next slide, so I'll just skip that for now. It's got one program there, program A. We've got another one, program B, and inside program A, which is then unfolded, program B is still folded. We can't see what's inside. Program A has 3 routines, A, B, and C. You can see that from the icons that there are also different types of programs. This one is ladder logic, this one is ladder logic, and that one is functional block diagram. It's just to show what kind of programming language is used in that particular routine. Then we've got tags, we've got program-specific tags. Now these are the variables or the memory locations that we're going to use inside that particular program. Then let me just scroll back one more, this one here. You'll see over there right on top we've got controller tags. Now these are then for the whole controller, for the whole PLC. All of these programs, tasks, routines, all of them can then access the tags that are defined for the whole controller. You can think of this as global variables in other programming languages. And then you've got tags for the program and that are more specific. So the other programs won't be able to see that particular program's tags. So program tags for program A will not be visible to program B, and so on. Very efficient way of grouping different or grouping the operation of a PLC. It's extremely well thought of, very clever. So the tasks, they are high level, they are a scheduling mechanism. We've got 3 different types. We'll see this on the next slide. Programs, they house the routines. They can have, you can have several programs inside a routine. So the actual code, then, where we do our programming, that is inside the routines. And they can be in any one of the 4 programming languages. Right, here we go. There are 3 different types of tasks. You can see the different icons. This one here with a looping arrow, this is the continuous type, which is the default, and the one that's most often used in PLC programming is a continuous loop. We've already discussed this. Then we've got a periodic one. This is something like monitor the tank level every second, or something like that. Then that is run on a timer, and it basically, you can think of this as an interrupt or a watchdog timer in microprocessor speak. So yeah, then every second this task will execute, and then it jumps to very high priority, so it will just push any other tasks to lower priority. Event-based tasks, these are triggered by something that happens, maybe some preset value, alarm or something like that. Will trigger the event-based task, and it will then also override the others in terms of priority. So these are the 3 different types of tasks. Right now, we've already looked at the different types in the family, in the Logix5000 family. So the Controllogix and also the software version, which we will be working with, can have 32 different tasks, but only one of them can be continuous tasks. So it does make sense though, because running 2 consecutive or 2 simultaneous continuous cycles, it simply doesn't make sense. One will always interfere with the other one. So all of them, you'll see that one will be able to run as a continuous task. Right, so in the the compact Logix, we can have between 4 and 32, depending on the exact model, and then drive logic up to 8 different tasks. Now within tasks, we've got programs. So we can up to 100 programs can be created in each task. Now remember, you've got 32 tasks, 100 programs per task, so you've already got 3,200 programs. So then you can then schedule the programs in whatever order you want, and there's also logic possible in the program execution. Okay, and then remember, inside programs we have routines, and each program can have up to 65,000 routines. So you can just imagine the staggering amount of routines available. Let me just give you the maximum. So it's 65535 routines per program. We've got 100 programs, and we've got 32 different tasks. This gives us this staggering number of 209 million different routines that can run on a Controllogix PLC. It's incredible, and can control a very, very large plant by one of these. Okay, and then a remark on unscheduled programs. This is simply a convenient place to park programs that you don't want to run. So it's just a storage space or a warehouse where you can store programs that you are perhaps working on, or maybe they are programs for fault finding or diagnostics that you don't run often, so they are unscheduled, but you do need them from time to time. So some draft programs or something, so you can store them there, and they won't interfere with the rest of the functionality. Alright, so we've got the 4 languages, ladder logic, the primary one, then we've got the FPD, functional block diagrams, HT, structured text, and then SFC, sequential function charts. Yeah, and they are 4 of the 6, that is the number, or the 6 languages defined by the IEC. So ladder logic looks like this. We've got 4 rungs in this case. The inputs usually have these square shapes in the symbols, and the outputs usually have these semi-circle type shapes. This is a retentive timer, RTO block in rung number 1, or rung number 0, but the first rung. Okay, function block diagram. These are very similar to just logical block diagrams that we are used to as engineers. It's a very common way of programming graphically. And then we've got sequential flowcharts, and in this case it's combined here with the structured text. So these 2 languages are here combined together. So structured text, very similar to Pascal programming language, and it's quite easy to learn. Actually, all 4 of these languages are pretty easy to learn. They are very powerful. They have their own pros and cons, but the one that's most often used is the ladder logic, and we will also then focus on this language. Okay, right, so that's the end of module 1. I'm going to remove these slides and then load these slides for module 2. If you just bear with me a minute. Just give me a second to load it for you. Shouldn't take too long. Right, it's loading now. Right, so here we go now with module 2, which is then still part of webinar number 1. So now we are moving along to the actual starting of a project in the Logix5000 platform by Alan Bradley. Right, so when we start a project, we create a new one. We give it some kind of a name that's descriptive, like control tank level or something like this, something that we can understand and that the next person will be able to decipher as well. Then what we define next is the controller type, Controllogix, and etc. etc. The different model numbers and so we'll define firmware version. This is very important because there are substantial differences in the different firmware upgrades. The slot number and then the file name. File name is usually the same or related to the project name, so that you can also see from the file name what the actual function is of this particular program or project. And we've already seen that we have tasks that contain programs and programs contain routines. And routines are actually where we're going to do the programming, but we do define specific tags within the program, but we can also define global tags at the controller level. So before we continue, we just have a look at some Nova systems. I'm sure you're all familiar with these definitions, but you just go through it to be complete. 1 bit in digital terminology is an information element that can either be a 0 or a 1, or an on and off in terms of relay speak. Then we've got when we build up digital information, we have several bits together, and the one that has the smallest value or represents the smallest value will be the LSB, the least significant bit. On the other hand, the one that represents the largest value will be MSB, the most significant bit. A byte is a group of 8 bits, a nibble is a group of 4, and a word is a group of 16. Then you have a double word, which is simply 2 words, and therefore 16 times 2, 32 bits of information. Right, we've got several other numbering systems apart from binary. Binary can only be 1s and 0s. Let me give you an example of a binary number just down here. Something like that will be a binary number, so it is not very easy for humans to understand, but machines work well with that. But to convert from this to something that humans can understand, we can convert to decimal, or we can convert to hexadecimal. And it's not very difficult to do. The thing is just like every bit of information, as you continue leftwards, every bit increases in the significance. So the first one carries a significance of 1, so it also in decimal terminology. The second one carries a significance of 2, which is 2 to the power of 1. The third one carries a significance of 4, which is 2 to the power of 2. So it's always a power of 2 to the left. So let's look at this example. So all of our digits are 1. So we've got 8 1s in our digital byte. The whole byte has 8 bits that are all 1. Now they are then power of 2, so there's 2 to the power of 0, which is 1, 2 to the power of 1, which is 2, and then 4, then 8, then 16, then 32, 64, and 128. So if all of them are 1, you add them all together, you get 255. Now remember, 0 is also possible, and therefore the total number of combinations in 8-bit or a byte is 256. Then in 16-bit you just carry on, so 2 to the power of 9, and then 10, and so you carry on until you have 2 to the power of 32, which is 32,000. And then if you add them all together, you'll get 65,000, which is then the representative of a double byte or a word. Right now, 16. Sorry, it's a 16-bit will be a word. Yes, correct. And then you have another numbering system which is hexadecimal. Hexadecimal is very easy to understand. It's just an extension that's changed to blue. So in decimal we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And what happens is, okay, we already have 10 digits, so it's decimal. What happens if we want to go above this number 9? We run out of numerical digits, so we start using alphabetical digits. So A, B, C, D, E, and the highest number is F. So we have now 16, and therefore we call it hexadecimal, because it's decimal plus 6. So decimal plus hexa, which is Greek for 6. Right, so we've got 16 different digits in this numbering system. And then it's simple to convert from from binary to hexadecimal. You simply do the same thing as above. And then just instead of stopping at 9, we just start numbering alphabetically from A to F. Yeah, and this is just described in text. We go into the alphabet for 10 and 15, or between 10 and 15. Yes, that's it for the basics of numbering systems. Let's continue to talk a little bit about tags. Well, tags are unique to the Logix 5000 system, unique to Adam Bradley. The idea behind them, as I said, I think in Module 1, is to facilitate the programming process by removing the direct or low-level memory addressing process. So then the software will actually take care of what is stored where, and you just simply use tags or human-readable memory names. So then we've got normal tags, normal memory location names. We've got tag arrays, which speaks for itself, and then alias tags is simply another name for the same tag. Okay, so they are then names used to define the area of memory, and we do not have direct addressing as in other PLCs. So a dint or a double integer is the default data type, which is 32 bits. And we'll see on, maybe I should jump to this slide. So you'll see the dint double integer, which is a 32-bit data type, is the default. And the real numbers are also stored using 32 bits. Ints are only 16-bit integers, and short ints are only 8 bits, and the boolean, of course, is only 1 bit. Okay, so this is even if you have a boolean, you use a complete dint. So you use 32 bits. So you waste some bits, but there's some clever ways of utilizing the unused space by using compound variables like or user-defined variables, but there's some built-in ones like timer variables. I'll show you one example. Well, yeah, we can have a look at the timer example. We have actually the timer value and then 3 boolean types indicating overflow and things like that. So that's a compound variable, where 3 booleans will be packed into one of the dints, saving some space. Saving quite a lot of space, actually. Okay, so have a look over here. You'll see this yellow part there. It's a dint storing the drive speed, which is a floating point number, a real number. Over here we've got a stop bit, yes or no, or a start bit, yes or no, a 0 or a 1. So we're wasting 31 bits of information in each case. So you can combine them, build a user-defined data type if you want. If you have lots of memory available in your controller, it doesn't really matter. It's just to save some memory space. So let's look at the different data types. Boolean, of course, very easy. It's a single bit of information, 1 or 0. short int we've seen on another slide is 8 bits between -1 to 8 and +1 to 7, so it's signed. If it's unsigned, but we don't have unsigned in Allen Bradley PLCs, it would have been from 0 to 255, as we've seen in the definition. So what we do is just shift everything so that 0 is in the middle, and then we have a plus and a minus part of the 8-bit number, so the int is between these two numbers. Int is 16-bit, so we've got -32,000 and +32,000. It would have been 65,535, but now, of course, we shifted it, so we have negative and positive numbers. dint is 32 bits. You can see -2 billion to +2 billion over there. Long int is a 64-bit signed integers. It's extremely long. It's really long number. It's not often used. Real number is a 32-bit floating point value. So this is an integer. This is a floating point number. And then the string, of course, is characters, ASCII data. Then we've got the structured or compound data types. I did mention this a few slides ago. For example, a counter will have a real number. If it counts seconds or milliseconds, for example, I'm talking about the timer, then it will be real numbers. If it's simply a counter, it will count in integers. Then you've got control variables, you've got message variables that will contain one or, well, at least two of the base variable types. Say, for example, a message will contain string, and it will also contain perhaps the int or int showing the message length or other information stored in that particular compound or structured data type. Okay, we have seen this before. We just see how many bytes or how many bits we actually use in the different types. Okay, so tags, I just mentioned it briefly. In one of the previous slides, we've seen just on the project tree that we have tags for the whole controller. So these are like global variables, and we also have program scoped tags. So remember that example? We had program A with its own tags that were invisible to program B, and vice versa. So when we define a tag, of course, we need to give it a name. We need to say what data type it is, the display style, data access control, and description. These last two are optional. Usually we don't use them. Especially in our examples, we probably, we won't use those last two. But the specific addressing we don't care about, because the software will do the addressing. So this is the beauty of the tag system. Right, in the RSLogix5000 system, we can call up a window, the control tag collection window, where we can see all the tags in the particular running system, or in that particular controller. So you can see different columns here in the name, alias, what type of tag. Is it a base tag? What kind of data type it is, a description, the access, and the style, and so on. These last few, they're not the display styles, just how we actually display this variable on the screen. And these data access control and description, they're usually not used, so you don't have to use them. Okay, now as you see on the left, you see some of these variable or tags, they are actually folded. Now this means they are structured, and then if you click on this, it will unfold, and it will give you the different tags inside, all the different variables inside a particular tag. So you can see the data type for this particular tag is compound. So when you open it up, it will change to more base data types, like over there. So if you want to have a look at this in real life, when I show you the Electromeet version of the remote lab software running. Right, yeah, this is just a zoomed in version, the alias tag name. Just talking about more aliases. This is an alias, another tag name. It's an alias for this tag. You can see this tag is not so easy to understand, so we give it another name that's more human readable. Like D valve closed is way easier to remember or to work with than this tag name. And then the base tag, of course, is the alias for name as well, and then the data type. And how we want to display it is in a decimal format. This is an error window if you want to look at tag verification. Maybe there, just for some fault finding or debugging, we can have a look at the tag verification window. Yes, and then just once again another screenshot of the tag collection window. Several things that you can do. You can right click, you can expand them as I've shown you before. Then we've got two tabs here, monitor tags and edit tags. You can actually change them in the edit tag window, or you can simply just monitor them, and as the program is running, you will see the actual value changing. So these can change from 1 to 0 live as the program is running. And then we have a watch tab where we can look at the tags and the variables inside the PLC, just like a window into what's going on inside the PLC, giving us the snapshot of the actual variable values in the system. Yeah, and then you can there's a current routine default view. And then we can also customize, so we can use a quick watch where we customize the just select some of these that we are actually interested in and ignore the rest, and so we don't have to have a full screen. We only use the ones that we really want to see. And then there's just another software module running called RSLogix. We will see that also. It's actually a communications or a link software component that links the emulator to the programming software. And then within this linking program, you can also look at the instantaneous values of the different tags in the defined in the controller. And then lastly, PLC addressing. As we said before, Logix5000 uses tags. Tags are human readable. Just a warning, perhaps. The comments and descriptions are not downloaded to the controller, but the tag names are. So if you're very descriptive of the tag names, you have at least that. So then you take the controller perhaps to another computer that doesn't have the program. You can upload the program into your new laptop or computer. Desktop computer, use the program. Then you have lost the comments and descriptions, but you haven't lost the tag names. So that's perhaps something that just needs to be remembered. Yeah, and this is just how the PLC addressing works: file type, file number, element number, and the bit number. Okay. Then what I'd like to quickly do is switch over to Electrometer. Maybe give me 1 or 2 seconds, so I can just give you a quick live demonstration. Okay, here we are. I'm going to do application sharing, which means I'm sharing one of the applications running on my computer. There you go. It's Chrome. It's my browser. Now you can see this address here. It's also in the instructions. You can find this in a PDF file that's already on Moodle. It shows you how to use the remote labs. So it gives you also the link that's live. So you control click, then your browser will automatically open with this Electrometer HTML5 web page. Right, then you enter your username. You don't use a password, so I usually use my name and first letter of my surname. Then I log in. You don't have to look at all of this. This is just a screen showing you some a short tutorial of what you can do. I'm just going to close that. What I am interested in, as you can see, then we've got different options here in Electromeet. I am interested in Remote Lab, so I click over there. We are running our software in Remote Lab number 12. It gives us a 60-minute time limit, and you can see we've got these types of software running on that particular machine. So what we then do is we click on the spanner, which is the VNC control function. You could also do a VNC view, so you could just watch someone else working on the system. But we're going to log in. We want to use the computer, so I just click on this, and then it will ask me for a password. The password